what's up, YouTube? Sorry about the few seconds of silence. I know everybody's already clicked away by now. Dang it, I just ruined another video. Oh well. For those who have stuck through that painful 10 seconds of silence, hello, my name is John. Today we're going to be practicing eigenvalues and eigenvectors. We are studying linear algebra and other mathematics live here on YouTube. So we are live momentarily. People will start showing up in the chat and we will get started. So, if you're watching the VOD, please let me know what would you like to see out of a channel like this. I think it's a really cool idea, personally. I think it's nice. We're building like a nice little community of math people, and I think it's pretty amazing. So, as I said, eigenvalues and eigenvectors. Today, here are some of the problems that we're going to work. We've got one just finding characteristic polynomial, solving that characteristic polynomial, and then finding the solutions to those equations, which are called the eigenvectors. Then we have diagonalization problem. After you find that eigenvalues and eigenvectors of a matrix, then you can also construct two other matrices, D and C, which will satisfy this equation. This process is called diagonalization. Then, after that, I've got a problem about applications. So we have a recursive sequence. A0 is 0, A1 is 1, and then AK is a combination of the previous two terms. So this is kind of like some sort of weighted Fibonacci sequence, kind of. It's like weighted Fibonacci. And we are going to diagonalize this matrix. After you diagonalize, then you get this really nice, convenient equation where the power of the matrix times the vector splits into the eigenspace. So we calculate the coordinate vector relative to the eigenvector, to the eigenbasis, and then we have this formula, d1 lambda 1 to the k v1 plus dot 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 dn lambda n to the k vn. And then once we have that formula, we can estimate the limit of the sequence for large K. We can find an estimation for a large term of that sequence. And of course, for the Fibonacci numbers, we get the beautiful golden ratio that pops out. Knock, knock. What's up, Levi? How's it going, man? So let's get into it, shall we? So let's just copy this first problem all over again. Thank you for tuning in to my practice stream, everybody. I hope you're having a great day. Let's switch over to the full screen. Knock, knock. Threads. What is threads? I'm doing good. How are you doing? I'm doing great, man. I'm doing great. Yeah. We're just telling knock, knock jokes right now in the chat. That's chill. All right, so thank you for tuning in. Let's get into it. Oh, wow. Okay. You had very loud music going, didn't you, this whole time? Oops. Okay, I did not intend to. There must have been like double music happening. Was there like double music just happening just now? Ah, streaming is hard. Streaming is hard. It's because I stream vertically and horizontally on two different channels, and it's really easy to mess that up. All right, well, oh well. Solution. It's so annoying when that happens. Okay, so we solve determinant of a minus lambda I to be the characteristic polynomial. And we solve that equal to 0. Let's rearrange a little bit. Change my mind. Let's do it like this. P of lambda equals determinant of a minus lambda I equals 0. So, yeah, you got double music. I apologize. That's so annoying. And one of them was very loud too, right? Like full volume. Okay, well, streaming is hard. Streaming is hard. We should just start over, right? Nah, whatever. Okay. So determinant of lambda I, a minus lambda I, is the determinant of 2 minus lambda, 0, 0, 1, negative 1 minus lambda, negative 2, negative 1, 0, 1 minus lambda. And this is 2 minus lambda times, well, yeah, 2 minus lambda times negative 1 minus lambda times 1 minus lambda. And that's it. I can see that because the minor matrix in the bottom right corner, the 2 by 2 minor matrix, the determinant is the product across the diagonal minus 0. So there we go. We're already done. So this I would rewrite as negative lambda minus 2, lambda plus 1, lambda minus 1. Then, thus, lambda 1, I like to go in, I like these to be sorted in ascending order. So lambda 1 is negative 1, lambda 2 is positive 1, and lambda 3 is positive 2. So this is part 1 to this question. Good morning, Real Deal. How's it going, dude? Good morning, Levi. Good morning, everybody. I hope you're doing well. I hope you're excited for another day of eigenvalue eigenvectors. Again and again, forever. Thus, we solve for V1, V2, V3 corresponding to the eigenvalues. So when lambda 1 is negative 1, then we're solving this equation. AV1 equals negative 1 times V1, which implies this system of equations. 2 minus negative 1 is 3, 0, 0, 1, minus 1 minus negative 1 is 0, negative 2, negative 1, 0, 1 minus negative 1 is positive 2. So we're computing the null space of this matrix. I will write null space as solving that matrix times a vector equals the 0 vector. And then, well, this implies that the first entry has to be equal to 0. And then that gets us we can subtract from the second equation 0, 0, 1, 0, and then the last term is, the last equation is identical, is -1 times the second row. So we have one free variable. Therefore, really, the eigenvector corresponding to -1. I should be putting the value of the eigenvalue here. The eigenvector corresponding to -1 is 0, 1, 0. So then next, the eigenvector corresponding to +1 A V1 equals V1. Then we solve the same type of system of equations. 2 minus 1. I'm comparing to this matrix where I've already, even though it's written as the determinant of the matrix, you can still see that as the correct matrix when we're solving for the null space of A minus lambda I. So 2 minus 1 is 1. 1 minus 1 minus 1 is -2. -2. -1, 0. 1 minus 1 is 0. This row reduces in a way where the last row is dependent on the first row. And we can zero out. So the first row is beautiful. It shows that the first coordinate is 0. And then we can remove that from the second line, that entry from the second line. So then, therefore, our eigenvector corresponding to eigenvalue 1 is 0. I see z as the free variable, the third component as the free variable. So when that is 1, then the second component is -1. But you can flip this. You could multiply that by -1 and it's still an eigenvector. So yeah, this, for anyone who hasn't seen this block of numbers with a bar and a solution on the right-hand side corresponds to this system. x1 is equal to 0, x2 plus x3 equals 0. So if I let x3 equal 1, then x2, after you subtract x3, x2 is -x3. So if I wanted to be a little more, just show that step in one step a bit better, I could have said 0, -x3 for any x3, or I could take specifically one value, like that. Cool. So any multiple of that is also an eigenvector corresponding to that eigenvalue. What's up, everybody? What's up? So now, finally, we have an eigenvector corresponding to eigenvalue 2. We're solving A V2 equals 2V2. I don't know if I like the subscripts that equal the value of the eigenvalue, but that's what I've seen in other books that I'm starting to work as well. So This implies the system of equations 0, 0, 0, 1, -3, -2, -1, 0, 1 minus 2 is -1. Okay, this one's a little bit more interesting to me. So rearranging, x plus z equals 0. I can combine that with a second equation to get that. And then I interchange the first and third rows, so the first row is now in that last row. Sure. This corresponds to this next set of equations like this. So therefore, our eigenvector corresponding to eigenvalue 2 is equal to x is -z. I'll use z. Why not z? -z. Y also equals -z. And z can be anything. So in particular, I can take -1, -1, 1. Or 1, 1, -1 also works. So those are our 3 eigenvectors. And I think that we're all done with this problem. Yeah. Find the characteristic polynomial, p of lambda, we did that. The real eigenvalues, those were the lambda that solve p lambda equals 0. So the roots of the characteristic polynomial. And the corresponding eigenvectors, we found those v lambda for this matrix. So we're all done. Cool. Next, we have a diagonalization problem. We're going to do the same type of beginning, at least, of the problem. So, yeah. How's it going, everybody? Anybody working these with me? I'm getting kind of tired of these like computation problems. I look forward to adding in more conceptual problems. Like we've seen these a few times. Maybe it's not the worst way to spend some time, but I am ready to move on soon. Solution. We could do 2 problems of each section today so that we can like get to more difficult material soon. Okay, so we do the same tricks. P of lambda, the characteristic polynomial. Let's see. It's going to be the determinant of -2 minus lambda, 0, -1, 0, 2 minus lambda, 0, 3, 0, 2 minus lambda. I can interchange the first and second rows. And we get this. So, yeah, nobody says that you have to do it exactly the same way. Or like that you're not allowed to do row operations while there's lambdas in the stuff. Do I stream real analysis? No, not yet. Would you want that? I'm starting to add calculus And I will have conceptual problems, including proofs. But it's still going to be calculus. It's not real analysis. I'm more of an algebra kind of person. But if that's what you want, we could do it. Okay, so we have the alternating sign, which cancels out with the sign in front of the determinant. Times -2 minus lambda minus 1, 3, 2 minus lambda. This is going to be 2 minus lambda times, I'm going to go ahead and factor out a -1 from this product. Lambda plus 2 times lambda minus 2 minus -3. Right? Now, this is going to be lambda squared minus 4 plus 3. Right? So now we can see all of our eigenvalues. Like that. Lambda squared minus 1 factors as lambda minus 1 times lambda plus 1. Yep. Thank you, Levi. I'm doing linear algebra, calculus, and representation theory in rotation. Yeah. Good way to put it. Yeah, I don't like real analysis. Like, if I'm doing math for fun, I'm not really interested. Dude, I don't like real analysis personally. But if you need calculus, dude, Sekar, we got calculus videos coming up. Therefore, I don't know. I like lambda 1. I like to just name the lambdas, like lambda 1, lambda 2, lambda 3. But, yeah, I don't know. What's the right way to write this stuff? Lambda 1 is -1. Our first eigenvalue is -1. Lambda 2 is +1. And our third eigenvalue is 2. Then our eigenvector corresponding to eigenvalue -1 is going to equal the solutions of the system. -2 minus -1 is -1, 0, -1. We're solving for the null space of the system. And why is that? It's because we're solving these equations that are like a v -1 equals -1 times v -1. We're solving this system of equations, which means that we can factor, or we can like add -1v to both sides, or add 1 times v to both sides. Then we get AV plus V equals 0. And then we can factor this out as A plus I times V equals 0. And now we're solving, this is solving that system of equations. So I'm adding the identity matrix to our original matrix A. 3, 0, 3. So this row reduces. The first and third equations are dependent on one another. 0, 0, 0, 0. And then the second equation is simple. So then, therefore, V, our eigenvector corresponding to -1 is -1, 0, 1. Watching from India, it's in my bachelor's syllabus. Thanks. Absolutely. What's up, Gagan Dabas? What's up? I'm happy to hear that I can help. Nice to meet you. We've got a few other people from India here in the chat. Cool. So now the second eigenvector is the set. It's the solution to A minus I, the null space of A minus I. So we have -3, 0, -1. Um, 0, 1, 0, 3, 0, 1. 0, 1, 0, 3, 0, 1. Yeah. 0, 1, 0, 3, 0, 1. 3, 0, 1. Can we do this directly? Can I solve this directly? I think I want to be able to. Okay, looking at that system of equations, the second term has to be 0. And then the first and third lines are dependent on one another. 3 times... So if x is 1, then z is -3. So there we go. I haven't learned advanced calculus properly myself. I haven't learned much undergrad stuff. Wow, you just jumped right to graduate level stuff? Levi, that's cool, dude. That's pretty cool. Levi, remind me, what's your deal, dude? Are you studying math at for fun as a hobby or something, or are you an engineer, or what's your deal, Levi? Our third eigenvector corresponds to lambda equals 2. So then we subtract 2i from matrix A. So -4, 0, -1. Let's keep our lives simple. The only entries that are different, that are changing, are along the diagonal, right? So I can at least write that out. That part is fixed. V1, I subtracted 1i, so if I subtract 2i, then I just need to subtract 1 more. There we go. So this is the system that we're solving. So V2, that doesn't look dependent. Oh, wait, no, it is. Yeah, it's a one-dimensional null space. Okay, from the third equation, from the third line, I see that the first component, x, has to equal 0. So x contributes nothing in the first line, therefore z equals 0 as well. And then the second component can be anything. Cool. So these are our three eigenvectors. Then C built from our eigenvector. I prefer to write them this way, with the subscripts being indexed. But for consistency, I guess I'll do v lambda 1, v lambda 2, v lambda 3. There we go. That'll fix my mismatch. Then our first eigenvector is -1, 0, 1. Our second eigenvector we found was 1, 0, -3. And then our third one was 1, 0, 1, 0. And our diagonal matrix should be -1, 1, 2, with zeros elsewhere. Should satisfy D equals C inverse AC, which is true if and only if CD equals AC. So we can just check this equation to avoid finding an inverse. Just slightly easier. So let's confirm that. Let's confirm. CD is equal to -1, 1, 0, 0, 0, 1, 1, -3, 0. Our diagonal matrix is -1, 0, 0, 0, 1, 0, 0, 0, 2. I think that means, I forget how to see this. I think that this means -1 times the first column, the second column is fixed, and then the third column is doubled. Is that true? I believe that you can see matrix multiplication that way. But let's see it. Multiplying those matrices together, we get +1. Yeah, and then I'm going to try to do this through to check my hypothesis here. So I'm going to calculate the first column first. 0 and then -1. Right? Yeah. I think that this is going to work. And then the first row, dot product second column, second row, dot product second column. It didn't work the way I thought it was going to work. No, it does. Yeah. Third row, dot product second column is -3. All right, first row and third column is 0, 2, and 0. So that was indeed -1 times the first column, 1 times the second column, and 2 times the third column. So Yeah, multiplying C times D should be pretty easy, generally. And now A times C, I have to remind myself what A is. I'm going to copy it here, but I still want it in blue because I'm a little OCD about that. Okay, let's get -2, 0, -1. It doesn't take very long to write. 0, 2, 0, 3, 0, 2 times matrix C, which I've already written right nearby. -1, 1, 0, 0, 0, 1, 1, -3, 0. If I multiply these matrices, I don't have a convenient diagonal matrix, but it's not too hard. We can do it. Let me read. I'm a second-year PhD student in algebraic geometry. Oh, sick. Okay, I didn't know that you're a PhD student. Okay, that makes me feel a little bit better. I don't know why I thought you were in high school, dude. And I thought you just knew all this stuff really well. And I was like, damn, I feel bad about myself. I need to up my game. Okay, cool. You're second year algebraic geometry. Let's go, dude. That's awesome. I love other fields of math too. I love them. For one, I like PDEs, number theory, and algebraic topology very much. Yeah, dude, I want to study some algebraic geometry. Bro, dude, it's nice to have you as a regular. I'm going to ask you 1,000 questions. The closest book I have to algebraic geometry is Eisenbud. I've got a view toward algebraic geometry, and we'll work this one on stream someday in theory. In theory, we'll do Eisenbud on stream. Am I into AI/ML? Not really. Dude, AI is so boring. AI took my job at Google. I worked at Google, and then AI took my job. AI took my job, and now I'm a YouTuber. Okay, so now we've got 2 minus 1 is 1. Learned some courses in physics too myself. Yeah, dude, let's go. I almost got a physics minor, but I didn't finish it. I was very close, though. I took quantum, the red and blue books in the top left of that bookshelf are, I think it's Shankar Quantum Mechanics, and definitely Jackson Electrodynamics. Jackson's scary, dude. Should we work Jackson on this stream someday? Whew, that would be scary as hell. Okay, so we double this. Oh wait, we take 1 times the first component and -3 times the second component. This entry is 0. Well, wait, what am I doing? I was going along the diagonal for some reason. -2 plus 3 is +1. Good. 0, 0, 0 in the top right. So everything matches so far. I feel pretty confident that we got this right. 0, 0, 0. 0, 2, 0, 2. -3 plus 2. Yep, we got this correct. 3 minus 6 is -3. We got this correct. 0, 0, 0. So notice those two matrices match, and then therefore CD equals AC, and then therefore D inverse equals C inverse AC. So let's freaking go. We're all done with this problem on diagonalization. Yeah, man, that's really cool, Levi. that you know some p-adic geometry and arithmetic geometry. I also have Sarah's course in arithmetic back there too. And I know that's kind of arithmetic geometry and some scary stuff. Those are scary books, dude. Yeah, that's awesome. I didn't realize. I thought that makes me feel pretty cool because you're watching me instead of K theory. Like I officially have one PhD student who watches me instead of K theory. Hell yeah. I'm jobless, so I can't take my job. JK, when are you streaming calc? We'll do calculus soon. So it's slow. It's very infrequent right now because I'm working in cycles. But in like 5 days or something, I think will be the next calculus stream. Is that what you want to see the most? We could just go on to the next chapter of linear algebra today. We're making good time and try to get back to calculus soon. Or if you want, I could do some calculus today. After I do all the problems from a section, I see the rest of the stream is just open to whatever I feel like working. Okay. Section 5.3, 2 applications. I'm sorry to hear that you're jobless. I kind of am. Kind of, in a sense, it's like this is my job, but I'm not really getting paid yet. So I feel you. Solution. Let this sequence be given by that for k greater than or equal to 2. So we want to find a matrix that captures this recurrence relation. And I need Eisenbud and Atiyah are standard. Everyone reads them. Yeah. I know Eisenbud is... Yeah, those two are like the standard ones, right? Isn't Eisenbud like the prerequisites? It's commutative algebra in prep for Atiyah, which in Atiyah McDonald? Is that right? Isn't Atiyah like the book in actual algebraic geometry, and like Eisenbud has a view toward algebraic geometry, right? But Atiyah, and that one I've heard that one is like newer, right? Like, isn't Ravi Vakil's The Rising Sea? That one did not exist when I was in school 15 years ago. I had not heard of that until like recently, until I saw K Theory's streams. But yeah, dude, I feel very honored that you're hanging out with me instead of him, even though he's doing like stuff that's way closer to what you're studying. Hell yeah. All right, so we want to find A equals A11, A12, A13. Since I'm using A for the sequence, so let's use, I don't know, alpha, beta, gamma, delta to prove that I know some Greek letters. Such that A times our initial vector, which for some reason I know is written as the most recent. Like, you could probably swap these two entries, but so far in the book, it's always put A1 up in the top entry. Let's write it this way, such that capital A times A1, A0 equals A2, A1. So, alpha times A1, let's see, so A2 should equal alpha A1, that's kind of cursed, but oh well, plus beta A naught. I get that from the first row of matrix A dot product with the vector, with the initial vector, and then A2 should equal gamma A1 plus delta A naught. I don't know if going to Greek letters was any better. Therefore, with our initial vector of 0, 1, and a k is 1/2. Here, let's copy this. I mean, you know K theory, right? Like he's starting to stream, and he streams at the exact same time as me. That scoundrel. So if y'all want to see some more complicated math, you could go watch that. I think he's working the Rising C. At least the Rising C is in his thumbnails. But, anyways, yeah. Let's chill. Then A2, I think that we can solve for alpha, beta, gamma, delta if we just calculate A2, which is 1/2 times A1 plus 3/16 times A naught, A0. And this is just going to be 1/2 times A1, which is 1. So can we get everything from this? I don't know if we can. Can we? Then alpha equals A2. Looking at that first line, because A naught is 0, and gamma equals A1. So alpha is 1/2. Gamma is 1. But we don't know beta and delta until we calculate the next term, I think. Because beta and delta could be, yeah, like right now we have a dependent system. Right? Yeah, we have a dependent system. Then if we take another equation, A3, we've already solved for what alpha is. A3 is alpha times A2 plus beta times A1. We know what A2 is. A2 is 1/2, and alpha is 1/2. So this is 1/4 plus beta times A1, which is 1. So, wait. Oh yeah, and A3 equals 1/2 times A2 plus 3/16 times A1, which is 1/2 times 1/2 and 3/16 times 1. So then this is A2 is 7/16, right? 7/16. So beta equals A3 minus 1/4. Beta is 3/16. And yeah, exactly. That's kind of part of my idea here, Levi. Like I want to hit exactly the right balance of like math that's just hard enough to be interesting, but not so hard that you're just like, I have no idea what's going on. I mean, and we're going to be going up and down, and it's going to be different audiences for which that difficulty level where that's in balance, right? For like somebody like you, like once we get into the later chapters of this book and its diagonalization and its change of basis and representation of matrices, conic sections, it's like, oh yeah, like I remember that, like, but it's not trivial. And then once we get into representation theory, it might be like, oh, this is like I have to learn a bit here. Although you probably, I don't know, does representation theory come up in your research or in your classes so far? But like you can follow along and like learn with me, even if you're not already like I'm sure you do, right? But like representation theory isn't exactly part of algebraic geometry, right? Yeah, not too easy, not too advanced, is like just hit the right balance. And for some people, that's going to be calculus. For some people, I want that to be like, okay, I never took calculus. I did okay in math in high school. I never really got it, but I think I could learn some calculus. Like it's just hard enough that, yeah, you get what I'm saying. What's a question I'm doing? What's up? How's it going? Milky the I do not know how to solve your question. You just asked about some crazy stuff. I am finding a matrix that represents this recurrence relation. And I think I know what it is, but like I'm pretty sure that we want I'm pretty sure it's going to be like 1/2 and 3/16 and then I think it's going to be 1 0 like this. I think that this is our matrix, but I want to get to this from first principles. This time around, I'm trying to like prove this matrix by first principles, and so far we found alpha here, and we found gamma here. So I'm pretty sure we're like nearly done. We're so close to done. Yeah. Yeah, we found alpha, gamma, beta. We just need one more. I want to show that delta is 0. And I have, in the second equation, for a squared, a2 needs to equal gamma a wait yeah gamma a1 no wait shoot I feel like there's a better way to prove this, but a2 equals oh yeah, a2 equals gamma a2 plus delta a1. Therefore, delta gamma. Yeah, let's just rewrite the whole equation. A2 we know is 1/2 and we're solving for gamma. And oh wait, no, we've already solved for gamma too. We've also solved for gamma, which is 1. We're solving for delta, and delta a1 we've already shown is equal to 1. So therefore, delta is 1/2 minus 1/2 is 0. And that's exactly what I wanted to find. That's exactly what I thought it would be. So I think that the form of these matrices, if we have, let's do R and S. If it's R a k minus 1 plus S times a k minus 2, I think that these matrices always are of the form RS 1 0. I think that these recurrence relations that are similar to Fibonacci sequences are always, I believe, of this form. And it matches for the Fibonacci numbers. R and S are both 1. Yeah. So, anyways, therefore, A is 1/2, 3/16, 1, and 0. No, you do not need representation theory until the field you were working in explicitly needs it, but I know representation theory good enough. Cool. So, yeah, you can follow along and help me out as I work some reps. Oh, your day's full of maths. Oh, you did Olympiad stuff. Dude, that's really cool, Levi. That's really cool. I would like to study some competition math. Dude, I would love to learn some competition math. I didn't do that in high school at all. Ta, I'm sorry to hear about your French exam. That sucks. Uh, hey, what's up, El Kukui? How are you, man? You're starting to study complex numbers from basics to advanced. Let's go, dude. Let's go. Um, Levi, you need representation theory in depth if you are like working in geometric representation theory. Yeah. I don't know. I just like linear algebra a lot. I don't know why I geek out about it so much. So I think representation theory. I like linear algebra, and I really like groups. Like in particular, I really like group theory out of like the abstract algebra sequence. So like, dude, it sounds like representation theory is exactly what I'm looking for, like what I should study if I like linear algebra and I like groups. Um, yeah, nice, El Kukui. That sounds like a fun endeavor. Okay, next we we can just simplify this as saying next we diagonalize A. Um, so the characteristic polynomial of A is going to be 1/2 minus lambda times negative lambda minus 3/16, which is lambda squared plus a half lambda minus 3/16. Okay, how can this factored out? Did I get that right? Why do I feel like I got that wrong? I'm going to pause for just a second, make sure I didn't make an oopsie. So I'm factoring out -1 from each of those product terms. Lambda times lambda minus 1/2. This is lambda squared minus a half lambda minus 3/16. Yeah, I think I made a mistake. What multiplies to 3/16 and adds to a half? I hope that it's a rational number. Well, we don't need to factor it in this form. We can say we solve for the roots through p of lambda, characteristic polynomial equals 0. So I don't need to factor it yet. This equals 0. Let's multiply the whole equation by 16. Then we get 16 lambda squared minus 8 lambda minus 3 equals 0. Is this easier to factor? I don't know, maybe. I don't know if this is any easier to factor, really, but one of these needs to be positive, and one of them needs to be negative, because they multiply to -3. One of them is most likely 3, and the other one is 1, because 3 is prime. So we want terms that 2 times 3 is 6. 6 and then 8. No. 16 rational root theorem would say that our possible rational roots are divisors of 3 divided by divisors of 16. So our possibilities are these. So I could... Oh, wait, I forgot 4. Yeah, I feel like 4 is a good contender here. These are all of our possible rational roots. It's just kind of a puzzle, isn't it? Let's see. Dude, we can just solve this with a quadratic equation, because it's a quadratic. So why are we doing this? We could just solve it with a quadratic equation. So I wouldn't even rewrite it. Let's just go straight to our original plus and minus the square root of b squared minus 4ac 3/4, right? 4 times a times c is 3 divided by 4. Yeah, I got that right. All over 2. And, well, voila. This is 1/2 plus and minus 1 over 2. And this is 3/2 over 2, or negative 1/2 over 2. So therefore, lambda 1 is 3/4, and lambda 2 is negative 1/4. These are our eigenvalues. Looking at the original and trying to confirm that, we have 9/16 minus 3/8 minus 3/16. That sounds about right. Yeah. Okay. I'm pretty sure I got those correct. I don't like competition math at all. It ruins the love for maths, and you just grind problems to improve scores. Yeah. Yeah, I feel you on that. Competition math seems like, practicing patterns a lot, but some of it does seem like real math, quote unquote. Like, I don't know. I don't know. Combinations and permutations. Let's go, Neuralize. Let's go. Yeah, like advanced, like college level researchy pure math feels so different from exam math, of like high school exam math or competition math. It's more creative, it's more slow, and you solve a problem for a week straight or something. Yeah. Well, dude, El Kukui, thanks for stopping by. Dude, thank you for stopping by. Okay, so we found the eigenvalues. Thus, well, yeah, we calculate eigenvectors. Our eigenvector corresponding to lambda equals 3/4 is going to be the null space of A minus 3/4. So negative 3/4 plus 1/2 would be negative 1/4. 3/16, 1, and negative 3/4. We should see that those two lines are linearly dependent, and that does seem to be true. Yep. So therefore, we have, so we're finding the null space of this matrix, which is the set of vectors, like if x okay, so if y is 1, then x is 3/4, and we can normalize that to, well, not normalize, but we can scale that to have integer solutions. And then v lambda 2 is our eigenvector corresponding to eigenvalue negative 1/4, which is the null space of a plus 1/4 is 3/4, 3/16, 1, and 1/4. So this, we're talking about the span of the vector again, if y is 1, then x is negative 1/4. And the span of that vector equals the span of negative 1/4, which is going to be easier to work with. So we diagonalize A as D equals C inverse AC. D is 3/4 and negative 1/4. There. I don't want to compute C inverse, I don't think. Can I avoid that? Hey, take care, dude. Thanks for stopping by, Levi. I apologize if I missed you. Thanks for stopping by. Have a great day. Okay. So we found a basis for the eigenspace, or we found an eigenbasis. So we can coordinatize a vector. So if we have a coordinate vector, do we have a guitar stream today? Yes, we will do one after the math stream. Probably after I solve this problem. If we have a coordinate vector, which I write as d1 through dn, and in this case it's just a coordinate vector d1, d2. We have the fact that ax is equal to a times d1 v1 plus d2 v2 for our eigenvectors v1, v2, which is equal to d1a v1 plus d2a v2 by linearity. And then that equals d1 lambda 1 v1 plus d2 lambda 2 v2. And a to the kx is similarly a to the k times d1 v1 plus d2 v2, and we get the same process, that this is d1 lambda 1 to the k v1 plus d2 lambda 2 to the k v2. So we coordinatize our initial vector a1, a0 because a to the k times our initial vector is equal to well, if k is 1, we want this to be a 2 on the top right. So this would be a k plus 1 a k. Right? So we solve for d1 v1 plus d2 v2 equals 1, 0. As the D1, V1. So 3, 4, negative 1, 4 solving with the solution 1, 0. Well, the second line simplifies, and like that. And then we can subtract 3 times that from the first line. So negative 1 minus 3 is negative 4. 1 minus 0. And then isn't that right? 1/4 and negative 1/4. Confirming that. 1/4 times 3, 4 minus 1/4 times negative 1, 4 is equal to 3/4 1 minus 1/4 1. Oh, wait. Here, plus 1/4, comma, negative 1. We correctly get 1, 0, and that's what we wanted. So, just confirmed our coordinatization. So, D1, let's say x relative to this basis is 1/4, negative 1/4. This is our coordinatization of the initial vector. And so, a to the k times x, which is equal to the k plus 1th term of the sequence in ak, is equal to 1/4 times lambda. Wait, let's write it out. D1 lambda 1 to the k times V1 plus D2 lambda 2 to the k V2, which is then 1/4 times lambda 1, which is lambda 1, where did I put it? 3/4 to the k times the vector, the eigenvector 3, 4, plus negative 1/4 times eigenvector, or eigenvalue negative 1/4 to the k times eigenvector negative 1, 4. Wow, so this term, this goes to 0. Neat. This problem asked us to confirm this for some values of k. When k is 0, I'll do this for k equals 0, k equal 1 and k equal 2. And I think that that should be enough. If k is 0, then the right-hand side equals 1/4 times 3/4 minus 1/4 times -1, 4. 3/4 plus 1/4 is 1. 1/4 minus 1. 1/4 minus, wait, what? No, 1 minus, 1 minus 1 is 0. Yeah, okay, there we go. When k is, and this correctly does equal a1, a0. So check, that worked. When k is equal to 1, the right-hand side is 1/4 times 3/4 times the eigenvector 3, 4. Let's give ourselves some more space, and let's try to do some of this in our heads. Let's skip ahead. So if k is 1, the second term is 3/4 times 1/4. This is 3/16 times eigenvector 3, 4 plus 1/16 times eigenvector -1, 4. Well, this would be 9/16 minus 1/16, which is then 8/16, which is 1/2. In the second component, 3/4 plus 1/4 is 1. And this is indeed A2, A1. So k equals 1 worked. And then when k is 2, we have 1/4 times 9/16. 9/16 times 1/4. 16 times 4 is 32/64, right? Minus 1/64 times the eigenvector -1, 4. Well, this would be 27/64 plus 1/64, which is 28/64. 28/64 is 14/32, which is 7/16. That sounds right? Hey, what's up? Good to see you, Sudeep. Welcome back. Really worth my time. Thanks. Thank you. Thank you. I'm glad you tuned in. What's up, Pana Makila? How are you? All right. Then 9/64 times 4 would be 9/16. Minus 1/16. And that would be 8/16, which is 1/2. Okay, so at least the second term I know is correct. I don't know if we ever calculated A3, but by definition, A3, wait, did I not do A3 anywhere? Oops. Did I never calculate A3? Let's just confirm it. By this definition, A3 is 1/2 A2 plus 3/16 times A1. And we've found A2 a few times is 1/2. So this would be 1/4 plus 3/16. A1 is 1. So this is 7/16. Yep, we got it. I think I got that somewhere. I think I wrote that somewhere. 7/16. Voila, that eigenvector decomposition or something worked out. Let's use a different color just for dopamine. Yeah, I'm glad it's worth your time, Pana. Thank you. Thank you for tuning in. I think it's worth my time too. I'm practicing. I'm getting better at math every day. Okay, so we've therefore confirmed that this diagonalization works. So, because d1 lambda 1 to the k v1 plus d2 lambda 2 to the k v2 we calculate the second component to find equation for AK. But before we even do this, we can classify first this generation process is stable because all eigenvalues have magnitude less than 1. Our eigenvalues are 3/4 and -1/4. And so either of those raised to a high power tends to 0. Like those are going to tend to 0 as k grows large. So the process is stable. I don't know if we need I don't know if it asks us to find the exact formula for AK. We found the matrix. We've classified as stable. We've computed this expression, I think. I mean, I've written down the expression. No, I don't think, I think it wants me to write the exact value. I don't know. And then use the answer to part C to estimate AK for large K. We are, I guess I would need to just do one more step. We could have answered this about the stability earlier, and I thought of it. It crossed my mind. I was like, oh, well, this process is stable. Both of the eigenvalues have magnitude less than 1. I thought that when we found the eigenvalues, but I didn't state it. So my exact solution here, I mean, we wrote it earlier, but it's 3/4 times 3/4 to the k. So this is 3/4 to the k plus 1. Okay. We have with that as the first component. In the second component, we have 3/4 to the k minus negative 1/4 to the k. Why am I... Why am I super nervous about the... Yeah, so this is minus negative 1/4 to the k. Yeah, I can't distribute that negative, right? Because if I distribute that negative, then we're always... Yeah, I can't distribute in that negative, right? Elementary row matrix. Yeah. What do you mean by that? Elementary row matrix. Why do I feel like I got this wrong? I think it's supposed to be this. I don't think I can distribute in another negative into the... Yeah, the first component definitely should be that. Negative 1/4 times negative 1/4 to the k is negative 1/4 to the k plus 1. And we subtract that from multiplying that last term. Okay. How do I explain eigenvectors to a newbie? I would just focus on the plane R2 and say that if you have a vector v, then in general, multiplying v by a matrix can move that vector to another place. It can rotate it, it can stretch it, you will get another vector somewhere in the plane after you multiply by a matrix. Eigenvectors and eigenvalues are special vectors where when you multiply it by that matrix, you get another vector on the same line. So it stays in the same line that it keeps the same angle that it originally had. It could go in the negative direction, and it might be shrunk instead of stretched, but it's still on the same line somewhere. So, yeah, I hope that answers your question. Can a 3x3 matrix be called a vector? No, a vector is a list of numbers. A vector is a list of numbers, x1 ... xn. A matrix and let's say that it's an m by n matrix, is a list of lists of numbers. So it's a double list. So a matrix is like a double vector or something. It's like a two-dimensional vector. It's a rectangle of numbers. I won't draw everything, but it's... So you asked about a 3x3 specifically. A 3x3 matrix is 3 rows and 3 columns. I'll use A11, A12, A13, A21, A22, A23, A31, A32, and A33. Like, for example, you could have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. That's a matrix. It's a block of 9 numbers. I hope that answers your question. Okay, so this is our exact formula for a to the k times x. And then in part D, as k tends to infinity, lambda 1 to the k tends to 0, and lambda 2 to the k tends to 0. So that seems super wrong, but I guess it makes sense. We're taking a half of the previous term and a 3/16 of the term before it, I guess that this sequence is shrinking over time, even though we're always adding positive numbers. That's pretty cool. Somehow that's actually kind of cool to me. Does it go up and then go down? Seven sixteenths is less than 1/2, so no. A4, the fourth term, I bet is even less. Yeah. That sequence is always going to reduce, I think. Anyways, yeah. Thank you for watching, everybody. Please do like and subscribe if you enjoyed this. Yeah, it was a pleasure hanging out and practicing math with you all live today. I doubt anybody's ever going to watch the VOD all the way to the end, but if you do, please let me know. It's a joy to be practicing math on the internet. Like how nerdy is that, dude? How nerdy is that? And I see we just crossed 1,100 subscribers, so let's go. That's awesome. Thank you for watching, everyone. Please do like and subscribe. I will do a guitar stream in a little bit. I'm going to take a short break, and then we'll come back, and I will practice classical guitar on my primary channel. So thanks for watching. I'm going to go now. Bye. Bye. Thanks for watching. Bye, everyone.